Hi, my name is Matt. I am the ecologist with the Watershed Center, and I'm going to help show you how to actually do this lesson. So the first thing I do is I take the group of students, usually 3 to 4 students is ideal, and we're going to move from wherever we were set up, whether it's a park bench or rocks or the ground next to the river, and we're just going to walk to the river, and I'm going to take some kind of collection tool. It could be a water bottle or this bucket, something that can hold about a half liter to a full liter of water, and we're just going to walk down to the river and make some observations first. So, this is the river that we're working with today. This is James Creek in Jamestown, Colorado. And I'm just going to get the students to make some observations first and foremost to try to get them thinking about how water quality can interact and be dependent on some of these things that we see around the river. So the first thing I'm going to ask them is to take note of what kind of vegetation is growing along the banks. So here at this location, there's actually not a lot of vegetation growing. Sometimes there may be lots of willows growing, grasses growing, full mature trees, and I just try to get them to notice that and ask them how they think that's going to influence water quality. There's really no right or wrong answers here. It's just to get them thinking about how things interact with each other. So that should only take 30 seconds or so to answer that question. Then I get them to focus on the river itself, and so I'll ask them, where do you see slow-moving water? Where do you see fast-moving water? Is the water clear, or is it cloudy? Is there sediment suspended in the water? What does the bottom of the river look like? Is it mostly sand? Is it mostly rocks? Is there algae growing on the river? Is there visible trash in the river or along the banks? Again, there's no right or wrong answers here, but students may start to make some interesting connections about trash being in the river influencing good or poor water quality, or even fast or slow water moving good or poor water quality. The only thing that we're going to be looking at today that might actually be influenced by some of these things is whether the water is slow or fast moving. Dissolved oxygen usually is higher in fast-moving water, where you see those white caps forming around rocks, and that's because oxygen is actually being transferred from the atmosphere into the water. So that's the first thing I tell them, is just make some observations. And that whole process, all those questions should maybe take 1 to 2 or maybe 3 minutes max. Then I'm going to ask a student to fill up the collection bucket with water, and again, students don't have to get wet. They can do this from the bank, or if they're wearing sandals or something, they can wade in a little bit. When they are filling up the water, I'll instruct them to just fill it up, try not to scrape the bottom. That said, if they do get some sediment and sand into the bucket, that's totally fine. The primary goal is really to be a scientist today and think like a scientist and go through this scientific process, not necessarily to collect the best results possible. So I'm going to fill this up. And I just filled up a nice clean thing of water. I just held it upstream and just dunked it in. And so now we're going to move the whole group over to our workstation with our water. I will probably also ask students, why are we even looking at water quality? Why is it important? And the primary reasons really are that water quality is important for humans because we drink it, we use it to water our crops, so it's important, we recreate in it, so it's important that it's clean. There are also insects that live in the water, there are also fish that live in the water, and we want to make sure that they have healthy populations and are living in clean, healthy water. So I'll say that at some point in that intro and as we're moving back to our workstation. So I'm just going to explain what we have in our bucket. Here, everything can fit in here pretty easily. First, we have a stopwatch to keep track of time. We have several different collection vials. The first is a small vial labeled DO, which stands for dissolved oxygen. We have a vial called, that's labeled pH, and there's a line up to the very top. We also have a vial that's labeled nitrate that is marked about halfway up. There is a non-translucent sleeve that the nitrate vial is actually going to fit into because sunlight can interfere with that test. We have a guide that shows different colors and different measurements that we're going to be comparing our results to actually come up with some quantitative numbers. And then we have different things that go in these vials. We have these tablets that you just push through here, and they're all labeled. We have pH, we have nitrate, we have dissolved oxygen, and then as a backup, we also have pH strips, which work in case you don't have pH tablets. And we're going to go through both of those today. And these are just extra pH tablets, or pH strips. And finally, we have the monitoring kit, which has some instructions here if you want to flip through that, but students don't necessarily need to have that on hand. So this whole lesson takes about 20 minutes from the talking all the way to doing the actual sampling, and time is rather tight. So right away, I get students working on some of these tests, and then as we're working through them, we're going to explain why we're doing what we're doing. Okay, so now we're actually going to start doing this sampling. The first is DO, so I'm going to have students be doing all of this, and I'm just instructing them on what to do. I'm going to have a student unscrew this vial, and we're going to fill this all the way up until it's actually overflowing. They can fill it up by pouring it in. The easiest way is actually to dunk it in and then take it out. And you want to see a little bubble forming on top. That's called the meniscus, and that just means there's no air bubbles and it's totally full. And while one student is doing that, I'm going to have another student pop out one of the tablets and drop that tablet in, and you're gonna, as you drop it in, you're gonna see some water overflow maybe. That's good, that means it's full. And then a student is going to cap it, and again some water may overflow, and that's fine. This test takes 5 minutes once the tablet dissolves, and it takes a couple minutes for this tablet to actually dissolve. So right away, I'm gonna have one student start shaking this pretty vigorously. And you're gonna find students will start really vigorously, and then they're gonna stop and get distracted by other things. And so you may have to remind them a couple times to keep shaking it, and do that for probably 1 to 2 or maybe even 3 minutes. So pretend the student is shaking that while we're moving on with the rest of the activity. While the DO is being shooken and the tablet is dissolving, we're gonna work on nitrate next. So again, you can pour water in. You can also just dunk it in. You can see I overfilled it. It's pretty easy to overfill it. So then just dump a little water out. And you want to get it as close to that line as possible, although it doesn't have to be exact. And then you're gonna have a student pop out one of the nitrate tabs. Dunk that in, cap it, and also start shaking this one. This test is also 5 minutes from once the tablet dissolves, and it takes a couple minutes for the tablet to dissolve. You also want to, as fast as you can, put it in this non-translucent sleeve so there's no sunlight hitting it, and have a student shake it up. The student's also shaking up the DO. While students are working on those two things, we're going to talk about why DO is important and why nitrate is important. So students may remember these terms from the previous in-class lesson, but you may have to remind them. First, I'll ask, why is dissolved oxygen important? And again, that's because insects and fish depend on it, and we want healthy fish populations. You can talk about where we're more likely to find higher dissolved oxygen areas, and those are going to be those faster moving areas where there's a little white water and more oxygen transfer happening between the atmosphere and the actual water. Then I'm going to talk about nitrate. I'll ask them if they've heard that term before, anything they know about it. Nitrate is most commonly found in fertilizers, so it's most likely coming into the stream from runoff from agricultural fields and other sources. It's not necessarily a bad thing because we do need nitrate to grow food, which we care about. But too high of levels could be bad and act as a pollutant towards fish populations, and humans also don't want to be drinking too much of it. So after we have those conversations, those are maybe a minute each or so. These are still being shooken up. Chances are the tablets have dissolved by that point. So now I'm going to have a student start a 5-minute timer. You could use a stopwatch, a phone, a watch, or whatever you have on hand. So now this stopwatch is going off for 5 minutes. I like to have one student in charge of the time, and I ask them to remind me every minute up until 5 minutes just to keep us on track. Once the tablets are dissolved and the timer's going, they don't need to be shaking it anymore because it's dissolved by that point, and it can just sit there and we're just waiting for that time to run out. Because those take the longest time, I do those first, and then I explain and talk about why they're important and why we're measuring them in the first place. Then I'm going to move on to pH. So this one is a much quicker test, so you can kind of talk about it simultaneously as students are working on it, or you can separate it if you want. Their students are going to fill this vial up to the very top, to where that line is, which is almost at the very top. And then we are going to drop a pH tablet in. And then cap it. And then have a student shake it up. This may take a minute or so. It's a lot faster than the others, and there's no waiting period once it dissolves. So while that's happening, I'll ask students why pH is important. pH is a measure of acidity in the water. Low acidity is, could be similar to lemon juice or vinegar. Higher acidity is that is basic when it's above 7, and that's going to be more similar to like a soapy liquid. So as this is going, we'll just let that go. You can continue talking about it. The normal drinking water is around 6 to 7. The aquatic life standard in Colorado for fish is between 6.5 and 9, so anything outside of those ranges is not healthy. That may depend on where you're exactly located though. And so one student will be working on that, and that can just sit there. We're going to compare it to the colors in just a minute. In case you don't have pH tablets, you can also use these strips, which are readily available online. And we're going to rip off one of these paper strips, dip it about halfway, 3/4 of the way into water, and then just let it dry for a minute or so. Once that dries, which happens quickly, you can compare it to the colors right on the box. And so right now, this is looking like it's about a 6. It may change a little bit as it dries. This is still a little wet. And just as a reminder, these are all in whole numbers, but if students think that maybe it's actually 6.5, it's not fully a 6 or not fully a 7, they can estimate in between those whole numbers to get as accurate of a number as they think. And that's usually a group activity, getting some consensus among the group until everyone agrees Is it a 6? Is it a 7? Or is it a 6.5? So this pH tablet has also dissolved by now. And we're just going to compare it to this color. So this test is showing maybe it's actually closer to a 7, kind of a pale green color. And then students can record 7 on their data sheet. Right now we're at 4 minutes on the time, so I'm always keeping aware of that. DO and nitrate, they're still working. If they're finished, you can move on to those. Usually they're still going, so now we're going to go to turbidity. In the kit that this came with, there's a line, and it's also on the inside. And we're just going to fill this bucket up to that line. And then inside the bucket, there is an image that is called a Secchi disc image, and it's just a circle that has white and black triangles. The cloudier the water that goes into this, the more unclear and opaque that image is going to be, and we're going to compare that color to our cheat sheet over here. So I ask a student to fill up to the line. You may have some extra water, which is fine. This is an instantaneous test. We're not dropping any tablets. We're just going to compare what that image at the bottom looks like to these images here. So 0 JTU means that there's 0 sediment in it. 100 means that there's a pretty good amount of sediment in there. You can see it's a lot harder to see. Again, the actual water rarely overlaps with any of these exact values, 0, 40, or 100. So I encourage students to estimate in between these. So right now, it's pretty close to 0. It's probably not exactly 0. So maybe I would say it's 5 JTU, and then I would record 5 on the data sheet. So we've hit 5 minutes. We've actually gone just a bit over, which is fine. So we can stop the watch. And now we're going to look at our DO first. It doesn't matter which one you look at first. But we're going to compare this color. So this is 0 ppm parts per million. If it's totally clear, there's no dissolved oxygen, and it can go 4 or 8 or even higher. Again, rarely it lines up with one of these exactly, so I encourage students to estimate. I would say this color is not exactly 4, but it's definitely greater than 0, so maybe I would estimate this to be 3. And again, I try to get students to get a consensus on that number. So I would record 3 ppm on the data sheet. Now, nitrate, same thing, we're just comparing the number to this middle column. We've got 5, 20, and 40. This is pretty clear, so it means there's not a lot of nitrate in here. It's not exactly totally clear, so it's not 0. Maybe I would estimate this to be 1 ppm of nitrate in this water. And so I would record 1 ppm on the data sheet. And we've gone through all of our tests, and that whole thing takes about 20 minutes.